Hey, everybody. So we're going to look at another application from physics, I guess, that we can use integration for. So this is something called moments and center of mass, and we'll get into what all of these things are. Center of mass you may have heard before, and I've got here our goal. This blue shape, we're imagining something just kind of any arbitrary shape that's flat, right? And it's consistent, the same thickness all the way through. And by flat, we just mean we can treat it like it's a two-dimensional object, but we're going to get there. We're going to get there. A center of mass would be the place where we can balance this thing, right? A point that you can put something under where it will all, where it won't tip over in any direction. So this is kind of a complicated idea, right? If you imagine kind of an abstract shape or an arbitrary shape, who knows what it looks like? How do you find this sort of, it's a kind of middle point when it's not something clear like a circle or a square or equilateral triangle or something like that. So that's our goal, right? As we often do, we're going to start with something very simple and build ourselves there. And this is actually kind of a long process. So I think we'll break this one up into a couple of videos. But it's a good process. Even if this isn't a topic of particular interest to you, the structure of thinking, the problem solving ideas that happen here, starting with something very simple, going through meticulously and adding on complexity as we go and learning from our previous steps is something that's a really, really good strategy, especially if you're approaching a new idea where there isn't a roadmap of how this thing works out, right? All right, so let's jump into it. So instead of starting with this big abstract shape, let's imagine something a bit simpler. Let's start with imagine a line. Sorry, let's start with two masses. All right, so I'll call this one M1, mass 1, this one mass 2. And let's assume it have this, they're on a bar. We're gonna say it's light enough that it's negligible, or in other words, we're gonna ignore it. And there's some point where this bar will be balanced, okay, right? So the masses aren't the same. If you've ever been on a seesaw, right? If the person you're on it with is significantly different mass than you are, you have to adjust how far away from you are from the center to find that balance, and that's kind of what's happening here. So let's label some things. I'll call the distance. Let's just label the distances from the center. We'll call the distance for M1 D1, and this distance from that balance point is going to be D2. And let's put these on a number line. Okay, so I'll call the coordinate for D1, or the location of M1, excuse me, on this number line, we'll call that X1. The coordinate for mass 2 is going to be X2, and we'll call this balance point X bar, right? So it's an X with a little bar above it. So by experiment, it has been determined that these masses will balance if the following property holds. If we have that the mass times the distance of one is equal to the mass times the distance of the other, okay? This is just a property of the universe. There's no can't give a good reason why. It's just a fundamental property of the universe. It's like, why do electrons and protons, or why are they attracted? They just are. That's just the rules of the universe. So here's one of our rules of the universe that we've determined from experiment. So we can rewrite this using the coordinate points, right? The distance is just the absolute value of each of these coordinates minus that X bar point in the middle. Notice if we use the traditional, the conventional way to use a number line, X1 is smaller than X bar. So when we take the absolute value, it's actually going to reverse this to make the subtraction to make it positive. whereas on this side, it won't have to do that thing, okay? So remember our ultimate goal. We were talking about finding the balance point of this arbitrary flat shape. We're starting by finding the balance point between two masses, okay? Much simpler idea. And if we take this equation here, we can solve this equation for x bar. I'll leave that algebra up to you. But if you work this out, x bar can be determined to be m1 x1 plus m2 x2 divided by m1 plus m2. Okay, so if your goal was to find the balance point, you have these two masses and you want to find the point in between them that would balance them. This gives us a way to do that. Okay, it gives us the coordinate of that, that point. So there's our first example of finding this balance point or center of mass. So let's throw some note or some vocabulary on here. We will call m1 times x1 and m2 times x2 the moments of the masses m1 and m2. So they each have their individual moment. And we will call m1 x1 plus m2 x2, that thing that showed up in the numerator there, is the first moment of the system, right? In this case, the system means these two masses considered together. The first moment of the system. We'll almost always not really worry about that first. We're not going into, there are things called a second and third moment and so on, but we're going to be focusing here. So for the purposes of these videos, this will just be the moment, okay? And then of course, we can say m1 plus m2 is the total mass of the system. Okay, and then x bar is the center of mass. Okay. It's a place where we could concentrate all of the mass. If we could somehow squeeze all of the mass into that point, it wouldn't change the moment of this system. And if you're in physics, you know that things like if you have two masses entwined somehow, determining their trajectory, you can treat them like a single mass at the center of mass in most cases, right? And so it offers a way to simplify sometimes complicated issues. So that's our first sort of simple version of this. Let's push it one bit further. If we have, let's say we have more than two masses. So let's say we have, if we have n masses, so m1, m2, on up to m sub n at positions x1, x2, on up to x sub n. So each mass is at some position. Then the center of mass, x bar of this system, and we would work it out in a very similar way. It's a bit more complicated, but can be worked out in a very similar way. We take the sum, right? Look at this equation up here. We have the sum of each mass times its position. We're going to do the same thing here. We're summing from 1 to n of x sub I. Let's write in the same order as the other one, sorry. Doesn't really matter, but let's just be consistent. It will be mi xi, right? So we're summing up the moment of each mass to get the moment of the system, and then dividing that by the total mass, right? Adding up each mass in the denominator there, okay? And this gives us the center of mass of objects on a line, right? Our picture here is we've got a horizontal line and these masses, right? We're really thinking them of like point masses, but I'm drawing them with different sizes so we get the idea that they're not all the same, right? If we had them distributed across this line, where's the point? Maybe about there, who knows, where these masses would be balanced. This is the center of mass of our system, okay? Just because you might experience this, you might come across this out there in the world, this term moment is extended into other realms. In particular, you'll see it in statistics, and it's very analogous to a mean, and that's how we use it. If you look at this this formula here, if you think of x sub I, the position, as let's say we're doing an average test score, right? Well, the x sub i's could be the scores, and the m sub i's are how many people got that score, and then we divide by the total number of people there are, right? This would be the formula for the mean test score. So in this case, the position is like the score, and the mass is like how much of that score is there, and then we divide by the total number of scores that there are. And that's why we think of this as like the middle. That's what a mean, one way to think about it is, it is the balance of all the scores. Okay, so there is our center of mass for objects on a line. Let's just write this. Sometimes we use capital M for the numerator to be the moment of the system, and lowercase m to be the total mass of the system, okay? All right, so let's go one step further with this. Let's complicate things just a little bit more. And now let's add a dimension to this, right? Right now we've got masses on a line. Let's put them in a plane, okay? So let's start with some axes, and let's put a mass out here somewhere, okay? So this mass, we're going to determine its moment, right? We were thinking before of relative to this balance point. We're still going to help ourselves find that balance point. But we're going to talk about moments with respect to the two axes. Okay? So in other words, this mass is some distance away from the y-axis and some distance away from the x-axis. And we'll call its moment with respect to the x-axis is m sub x, and we take the mass, so I'm just calling this mass m1, and it has coordinates x1, y1. We take its moment, so here's where it gets a little confusing. It's with respect to the x-axis. How far is it from the x-axis? Well, its distance is given by the y-coordinate. So the moment with respect to the x-axis has the y-coordinate in it, and the moment with respect, sorry, that got sloppy, to the y-axis is the mass times the x-coordinate. That's the distance from the y-axis, okay? So that's how we determine these moments when we have, there's a separate moment for the x and the y. And then of course, if I had more objects, they'd each have their own moments, right? Their own distances from the axes, okay? And so using what we had learned in the previous, kind of following the pattern from the last, from looking at things on a line. Now we're looking at objects in the plane. So we'll look at the center of mass of a system of objects in the plane. Okay. We'll start with objects, point masses M1, M2, up to Mn at points X1, Y1, X2, Y2, on up to Xn, Yn. So again, we have n points. Then we have the moment with respect to the x-axis. And this is going to be given by the sum of mi times yi. And the moment with respect to the y-axis is going to be the sum over all these masses of mi xi, right? So just like we did previously, we added them all up, but now we've got two different directions. What's happening in our horizontal direction and what's happening in our vertical direction. And so then we'll let little m be the total mass. Then the center of mass of this system is given by x bar is going to be my over little m, and y bar is going to be mx over little m. Okay, right? So notice that those x and y confusion there. This is the moment with respect to the y-axis, which means we're looking at how far we are away from the y-axis, which is horizontal, which is why it's the x bar, and then the same thing for the y bar, right? Which means the center of mass is, I forgot to write this here, given by the coordinates x bar, y bar. So if we have all these three masses that I've drawn up here, we might compute the center of mass and maybe it ends up here. And that's we can think of it as the balance point. If somehow these were, on some thin film that had no mass itself, and they were the only things weighing it down, that's where we could put our balance to keep them flat, right? Or in physics, we could treat them as a concentrated mass at that point and determine their trajectory that way, even if they're spinning and rotating around or something like that. Okay. All right, let's finish this video with an example. Let's find, oops, I wanted this to, for some reason that's bothering me that it's not very straight. Let's make it a little better. There we go. All right, let's do an example over here. We've got, let's find the moment, find the moments and the center of mass for the following system. We're going to have three masses. I'm going to give their mass and their position. So I had 3, 4, and 8. And the positions are -1, 1, 2, -1, and 3, 2. Okay, so I'll sketch it first. Sketch the situation. Just a quick sketch. Mostly this sketch is to help eyeball whether the answer I get makes sense, right? It's always nice to know if you've made some computational error. So maybe I'll just throw in a couple of hash marks here. More or less even, I think. I always make those first ones a little too far away. All right, so we've got a point at -1, 1. There's our point mass with mass 3, 2, -1, we've got a mass 4, and then 3, 2, we've got a mass of 8, right? So if you imagine these things, trying to find like the center of them with taking into account how there's a heavier point over here. If you kind of imagine the triangle, right? We can imagine the center of the triangle here, and I imagine it's going to be pulled towards that heavier side, right? We need to get closer to it to balance it. So maybe I'll just throw in there my eyeball estimate is somewhere in here, right? Really rough estimate. And all I'm going to see is if I get an x coordinate of 7, I'll know that I made some computational error. If I get an x coordinate of -1/2, I'll know I made a computational error, or at least be suspicious and want to double check my work, right? So it's nice to have a little estimate in there. All right, so let's get to work. We need, so I'm looking at this rule right here. We need, let's start with little m. This one's easy. Our total mass, we're just adding up all the masses. So we've got 3 plus 4 plus 8 is 15. I need to compute the moments. Let's start with mx, right? That's given right here, where we take each mass and multiply by its y coordinate. So we'll have 3 times 1 plus 4 times -1 plus 8 times 2, and we get 15. Right, 3 minus 4, sorry, yeah, 3 minus 4 plus 16 gives me 15. And then my, we take each mass, right? That's our formula here. We take each mass and multiply by the x coordinate. So we'll have 3 times -1 plus 4 times 2 plus 8 times 3 gives me 8 minus 3 is 5 plus 24 gives me 29. Okay, so there's the two moments. We've got 15 and 29. And now let's compute the center of mass. It's going to be given by x bar, which is m. So that's in this box here, my over m. So 29 over 15. And y bar, which is 15 over 15, or 1, right? So let's give approximate coordinates. 29 over 15 is just about 2. I'm just going to write about 2 and then 1, right? These are exact fractions. I just want to use this to see how it works with my my eyeball, and you can see my eyeballing was right at about 2, 1. I'd written it a little bit too far to the right and a little bit too high, but close enough for that eyeball approximation. And so this is our center of mass for the system. Okay, let's stop there. It's already a pretty complicated idea, and then we'll start moving into how do we take this, and instead of having point masses, we have whole plates of mass, these things that we'll call lambda. But that's for the next one. Okay, thanks everybody. I will see you next time.